This is a video for AQA Further Pure Mathematics, the Roots of Equations, section 1.5, where we're going to be looking at solving polynomials that have got complex roots. Well, for polynomials that do have complex roots, then those roots will occur in conjugate pairs if the polynomial has got real coefficients. And all of the examples we'll be looking at will have real coefficients. So that we can say that for any polynomial, if alpha is equal to a plus bi is a root of the polynomial, then beta, which is equal to a minus bi, its conjugate, must also be a root. Now we can then think about what does that mean in terms of a cubic. Well, a cubic will have 3 roots, and therefore there's either 1 real and 2 complex which are conjugates of each other, or all 3 roots will be real. We can also think about the other situations we have for quadratics, cubics and quartics. So you can see there the top graph is showing you the situation where we either have 2 real roots, so that the graph crosses the axis of the x-axis at 2 distinct points. It's possible that that could be repeated, so in other words then the graph would come down and just touch the x-axis, and that would be a repeated real root. Or if the graph is above, or indeed if it's a negative one and totally below the x-axis, so it doesn't touch the axis at all, then we'll have a pair of complex conjugate roots. So we either have 2 real or 2 complex, and there'll be a conjugate pair. For a cubic, I've got the situation where we have got in the first graph there 3 roots which are distinct. It's possible again, if it moves up a little bit, for that to be 1 real and then a repeated real. So for example, if we have a graph which comes up and then comes back down but just touches the graph, there we've got 3 roots, but one of them is repeated. In the right hand graph we've got a single real root where it crosses the axis, and then a conjugate pair of complex roots. For a quartic, similarly, 4 roots this time, so we could have 4 distinct. And again, you might like to think about how they may be repeated. So each of those paths which is crossing may just touch the axis to give you either 2 distinct and then, well, 2 distinct and a pair which are repeated, or in fact 2 repeated roots. The second diagram is a situation where we have a pair of real and then a pair of complex conjugate roots, and finally 2 pairs of complex conjugates. So there's no points where the quartic there is crossing the x-axis. So when it comes to working with polynomials that have got complex roots, then the key ideas that we will need to use are firstly that the complex roots occur in conjugate pairs, as long as the polynomial has real coefficients, and that will always be the case for the examples that we're looking at. We may wish to use, or may need to use, the factor theorem, so that if f of alpha is equal to 0, then x minus alpha is a factor of f of x. This is also true for the complex roots, so therefore, as I've already said, that if alpha is a plus bi, then beta is a minus bi must also be a root. And finally, we've got the relationship between alpha, beta, gamma, etc. and the coefficients, so looking at the sums and products of the roots. Well, here's a typical example then where we're given an equation az squared plus bz plus c equal to 0, and we're told that 1 root is 3 plus 2i, and also that a is equal to 1. And we're asked to find then the values of b and c. Now there are different methods of doing this, so I'll look at a couple of the different methods. Firstly, we can look at using the roots and coefficients. Well, we know then if one root alpha is equal to 3 plus 2i, then the other root beta must be equal to 3 minus 2i. So therefore we can find the sum of the roots alpha plus beta, and that's going to be equal to 3 plus 2i and plus 3 minus 2i, which is equal to 6. And we can also find the product alpha beta, which is 3 plus 2i multiplied by 3 minus 2i. And remember, when we've got conjugates multiplied together, then that's going to be equal to 3 squared plus 2 squared, so that's equal to 13. So the sum of the roots is equal to 6, and the sum of the roots is equal to minus b over a is equal to 6. And the product of the roots, alpha beta, is equal to c over a, so c over a is equal to 13. And therefore we can say that if a is equal to 1, our polynomial must therefore be z squared, and then we've got b is equal to negative 6, so minus 6z, and finally plus 13 is equal to 0. So to answer the question then that we've been asked, b is equal to negative 6 and c is equal to 13. Notice that it's not strictly necessary to write out the actual polynomial to be able to quote the values of b and c. So there it is on a nice neatly presented slide, so you might like to pause that and just make sure you're happy with the method there. Well, an alternative method to this is to use the idea of multiplying out the factors. So given that alpha was 3 plus 2i and beta 3 minus 2i, then we can write the polynomial as a product of its factors, so z minus alpha and z minus beta. So we get z minus 3 plus 2i and z minus 3 minus 2i. If you multiply that out, the first term z squared, and then we get minus 3 plus 2i and minus 3 minus 2i times z, or indeed just minus 6z. And finally those conjugates multiplied together, giving us plus 13. So again we have our values of b as negative 6 and c as being equal to 13. Well, now I'd like to look at a similar example, but this time involving a cubic equation, where we're told that one root of the equation z cubed plus 3z squared plus 12z plus 10 equal to 0 is minus 1 minus 3i. So again, different methods. I'm going to first of all look at the method of using the roots and coefficients. So this time we've got the similar sort of situation where if alpha is minus 1 minus 3i, the root that we're given, then beta must be minus 1 plus 3i. Well, we know that the sum of the roots, alpha plus beta plus gamma, is equal to minus b over a, so that must be equal to negative 3. But if we calculate alpha and beta, or we substitute for alpha and beta, we therefore get that minus 1 minus 3i plus minus 1 plus 3i plus gamma must be equal to negative 3. Or in other words, minus 2 plus gamma is equal to negative 3, and therefore we can see that gamma must be equal to negative 1. So that the roots are in total the one that we're given, -1 minus 3i, and the other roots are the conjugate of that, -1 plus 3i, and finally the real one, which is gamma, which is -1. And there again it is written out for you, so you can pause this and make sure you're happy with that solution. Well, an alternative method is to first of all make a quadratic factor by taking the factors z minus -1 minus 3i and z minus -1 plus 3i, so the two roots that we know, forming a quadratic from that, and then factorizing the cubic as a factor of the quadratic and a linear factor. The quadratic factor that we get is z squared plus 2z plus 10, and so that the cubic must be equal to z squared plus 2z plus 10 multiplied by a linear factor to give us the cubic z cubed plus 3z squared plus 12z plus 10. The linear factor is quite straightforward. Then we can see that the first part must be z, and then the second part, to give us 10 at the end, this must be plus 1. And therefore from that linear factor we can see that the other root must be z is equal to -1. Well, as a second example of a cubic equation, then we've got a cubic here where one of the roots is equal to 2 and we're asked to find the other roots. Well, if a root is equal to 2, then this means that z minus 2 must be a factor. And if that is the case, we can write the cubic z cubed minus 2z minus 4 as being equal to some quadratic multiplied by that linear factor z minus 2. So we need to calculate a quadratic factor. Now again, it's not too difficult to do this by inspection. So we can first of all see that the first term must be z squared, and that will give us the z cubed at the start, and that the final term, the number term, must be equal to plus 2 to give us -4 at the end. So we're left with just the middle term to calculate, and you can get that by considering the coefficients of z squared, for example. At the moment we've got minus 2z squared, so that we must therefore have in here plus 2z to give us a total of no z squared on the left hand side. So that's minus 2z squared is there, so this must be 2 plus 2z squared, so that the middle term here must be plus 2z. Now once we've got that quadratic, we can then factorize that, or we can find the roots. Perhaps the easiest way for this one, if z squared plus 2z plus 2 is equal to 0, is to use completing the square, so that z plus 1 all squared and then plus 1 is equal to 0, and therefore we get that z is equal to -1 plus or minus I, so that the other roots are a conjugate pair of -1 plus or minus I. So we can use similar methods to those that we looked at for quartics. In a quartic equation you might be given a complex root and asked to find the other root. So remember, once you've got one complex root, you've immediately got its conjugate as being another root. You might be given two real roots, and that will allow you to form a quadratic which you can then factorize the quartic into two quadratic equations. And you might occasionally need the factor theorem to be able to work out two real roots before you find any others. If you've got no other information, factor theorem would allow you to find two real roots. There are plenty of notes about this, these methods in Integral and also in your textbook. Well, that's the end of this video, and indeed it's the end of this section on roots of equations.